Welcome to the video lecture on the derivative and the tangent line problem. In this video lecture today, we're going to talk about a very important topic in calculus called the derivative. And the derivative was created to help address something called the tangent line problem. So that's where we're going to start today. Let's talk about what a tangent line to a circle at a point P means. So in geometry, when we talk about a tangent line to a circle, we have this point P on the rim of our circle, and the tangent line through that point P would intersect the circle exactly once, and if you were to draw a perpendicular radius from the center to that point P, you're forming a right angle. So this radius to our line through P is perpendicular. Okay? So we want to maintain that property of intersecting only once, but we're going to expand that idea to not just tangent lines to circles, but tangent lines to any curve whatsoever. So here we have just random curves that I've drawn, and we want to think about what it would mean to be a tangent line to one of these curves at any point P. So here we have our point P, and I sketched in what the tangent line might look like. And this sort of fits our image of what it means to be a tangent to a circle. We're just intersecting our curve at exactly one point P. Another sort of key idea behind this tangent line is that tangent line should sort of point us in the direction of the curve. And you can kind of see that in this next diagram over here. Again, this line is only intersecting this curve right at P, at least initially, from what I've drawn. And you can kind of imagine that this line is sort of pointing us in the direction that the curve is going to go. Similarly over here, this tangent line through P is intersecting only at point P, and it's sort of fitting the direction of the curve. Now you might say, well, what if I were to extend this line right here? Then it would actually hit in more than one spot, at P and then in this case down here as well. So what we are going to talk about when we do tangent lines is talking about the tangent line in a small window. So we're not necessarily going to look at the entire line and say that it can only intersect the curve once, because that may not be possible. But in a small neighborhood of P, in a small window around P, that line should intersect only at P. So a couple of the qualities here that we want to maintain is that the tangent line should intersect only at P. And this, again, is assuming that we are in a small window near P. So if we were to extend our line out, it's okay if that tangent line would cross in other places, but close to P, it should only be intersecting once, right at P. And then another key property that we want this tangent line to have is that it should also fit the direction of the curve. So it should fit the direction of the curve. And I kind of think of this as sort of leading us where we're going next. So if you want to think about a typical sort of real life example of a tangent line, imagine that you were driving a car in the middle of the night on a very curvy road. The direction that your headlights are pointing, they are sort of pointing you in the direction of the road, and the beam of those headlights is forming a tangent line. So headlights of a car on a dark night are fitting the direction of the curve, and they're sort of acting like a tangent line. So that's what we want to sort of maintain when we think about what is a tangent line to a curve. It should fit the direction of the curve, point us in the direction we're supposed to go, and it should only intersect our curve at that point P when we're talking about a small window around P. So let's look at a specific function. This function that we're looking at is negative 16x squared plus 16x plus 32. So it's a nice quadratic function, and here's what the graph of it looks like. Now let's illustrate what we believe to be a tangent line to the curve at the point 1, 32. So 1, 32 would be right about here. So there's our point P, and if we were going to draw in a tangent line that fits the direction of the curve and intersects only at P, you can see that at this point P the curve is tending to want to go down. So our line should point us in that downward direction and intersect only at that point P. And it's hard for me on my computer here to draw straight lines, so I'm going to ask you to use your imagination a little bit, but to me that looks like a pretty good tangent line. Okay, so there's what we might suspect the tangent line to look like, fitting the direction of the curve and intersecting only at P. So think about, what if we wanted to come up with the equation of this tangent line? Well, if you want the equation of a line, you need to know what its slope is. And so that's what we're going to be working very hard to calculate, the slope of this tangent line. And what is necessary to find a slope of a line? Well, if you want to find the slope of a line, you need to know 2 points, right? You need to know an x1, y1, and an x2, y2, so that you can calculate the change in the y's over the change in the x's. So if we're going to find the slope of this line, we are going to need 2 points. And once we have those 2 points, we'll be able to do our change in y over our change in x, or our y2 minus y1 over x2 minus x1. Now the good news is we know 1 point. We know point P. That's 1, 32. So we have 1 point already. The bad news is this tangent line only goes through 1 point. It's supposed to only intersect right at P. So we don't know a second point on this tangent line, since we don't even know the equation of this tangent line. So what's another way that we could come up with a second point so that we could figure out our slope? Well, what we're going to do is we're going to estimate our slope. We're not going to be able to necessarily find it exactly, at least not right away. What we're going to do instead is estimate the slope by potentially picking a point that should be pretty close to this tangent line. So what we're going to do is we're going to let our point P be this 1, 32, and then we're going to pick a second point, which I'm going to call point Q, that's close to P. And then we're going to calculate the slope between these 2 points. So calculate the slope between point P and Q. So imagine that I pick another point Q, and I want it to be pretty close to P so that I'm not creating a new line that's totally different than this tangent line. I want to be pretty close to my actual tangent line. So if I pick a point Q pretty close, then we can create this second line right here, which is actually called a secant line. Now a secant line by definition is just the line that connects 2 points on our function. So this point P we know is on our function 1, 32, and the point Q that I pick is also going to lie on this function. And once I know the coordinates of point Q, then I can do my change in y over my change in x and get a slope. Now that won't be the exact tangent line slope, it'll just be an approximation. And ideally, the closer that point Q is to P, the closer that approximation will be. So that's what we're going to do next. So let's explore an efficient way of calculating some of these slopes. We're going to let Q vary. We're going to pick these different points Q, getting closer and closer to point P, and hopefully those slopes of those secant lines will start to estimate the slope of that tangent line really, really well. So point P has this tangent line going through it. Now it's ideally what we're trying to get at, the slope of that tangent line, but what we can do to estimate it is we can pick some points Q like this and create a secant line. Now that point Q is pretty far away from P, and so you can see that these two lines, the red line and the blue line, are pretty far apart from each other. But the idea is if I pick another point Q that's closer, then this secant line is going to look more and more like that red line. And the closer I make Q get to P, the better the approximation will become. So let's see if we can do this. P is the point 1, 32, and I'm going to let Q be a point on f of x with coordinates x, f of x. So just some random point x, f of x. How do you find the slope of this secant line between P and Q? Well, remember that slope of a line is change in y over change in x. So all I have to do is take my two y coordinates of my point P and my point Q and subtract them, and then subtract my two x coordinates. So the y coordinate of point Q is this f of x, and the y coordinate of point P is this 32. So I want to subtract those two y values. On the bottom, I'm going to subtract my two x values. So this is the x value of my point Q, and 1 is the x value of my point P. So all I did was subtract my y's over subtracting my x's. So this kind of gives us a formula for calculating these secant line slopes, and I can pick my Q to be whatever I want. So let's go ahead and pick some Q's. Now remember, we're trying to pick our Q's close to point P, and point P is at 1, 32, so the x value is 1. So if we're going to pick Q's close to P, then we should let the x value of point Q be something close to 1. So here I'm going to let the x value of point Q be 0, and then I'm going to let it be a half, and then I'm going to let it be 1.5, and I'm going to let it be 2. So those are all fairly close to 1. Okay? So these are the x values of point Q. What are the y values, or the function values of this point Q? How do I find out what their y coordinates are? Well, that just requires using our function. So to find out what the coordinates of point Q are if x is 0, to find this y value, I'm just going to plug in 0 for each of these x's. So this would give me 0 plus 0 plus 32. So point Q would have to be 0, 32. Now that I know what that y value is, I can go ahead and use this slope formula right here to calculate the slope. So if point P is 1, 32, and point Q is 0, 32, then what would be the slope between those 2 points? Well, it's this f of x value minus this 32 over this x value minus 1. And 32 minus 32 is going to give me 0 over negative 1, which is just a slope of 0. So there's my first secant line and its slope. So let's sketch that one in up here. And that was when x was 0. So that would be like this point over here, point Q. And if we connect the line between point P and Q, and this is called a secant line when we connect our two lines, you can see that that's a horizontal line, and horizontal lines have slope 0. So it makes sense that we got 0 for that slope. Okay? So let's try this again with a better choice for Q. Let's not be quite so far away. On our next choice of Q, now we're going to let x be a half, which would be this point up here. And so you can see that that secant line, whatever its slope is, it should be a much better approximation to our red tangent line than our first choice was, which was horizontal. So let's calculate what this new secant slope is going to be. So this time, we are going to let our x value of our point Q be 1/2. and we want to find out what the y value of that point Q is. So again, all you have to do, these point Q's are always on your function. So to find the y values of your point Q, you always go back to your rule, your function rule, and you plug in that x value. So this would be negative 16 times 1/2 squared plus 16 times 1/2 plus 32. And I'm going to let you go ahead and plug that into your calculator to verify, but this turns out to be 36. So the y coordinate of point Q is 36. So if point P is 1, 32 and point Q is 1/2, 36, then the slope between these 2 points, I'm going to call that M sub PQ, would be the difference in this f of x minus this y value over the difference in our two x's. So 1/2 minus 1. And that gives me 4 over negative 1/2, which is negative 8. So the slope of this second black line right here was a slope of negative 8. Okay, so we're getting closer to that tangent line slope. All right, now let's try it again for a different choice of Q. So this time I'm going to let my Q have an x coordinate of 1.5. So this time on my graph, our point Q is on the other side of 1, and it's about here. So now we're looking at this tangent line right here, which looks, again, much closer to that red line than our horizontal secant line did. So this should be a better approximation. So to find the y value, to find this f of x, we're going to take 1.5 and we're just going to plug it into our function. So negative 16 times 1.5, which is 3/2 squared, plus 16 times 3/2 plus 32. And when you simplify that, it turns out to be 20. So then if my point P is 1, 32, then the slope between these 2 points would be this y minus this y, so 20 minus 32 over this x minus this x. So we're going to get negative 12 on top over 1/2 on the bottom, which when you flip over that 1/2 and multiply by the reciprocal gives me negative 24. So the slope of that secant line is negative 24. All right, let's try it one more time. This time we're going to let our point Q be at x equals to 2. So we're getting a little farther away from that point P. So we're going to let our x value be 2. So to find the y value of point Q, I'm just plugging in 2. And when you substitute that in, you do get 20 again. So when I find my slope between these 2 points, we're going to take this y minus this y, so 20 minus 32, over this x minus this x. So we get that negative 12 on top again, but on the bottom we just get 1. So this slope is negative 12. Okay? So as you can see, we can approximate these tangent line slopes by using secant lines. And the closer that we get to point Q, the better our approximation should be. But this is a pretty tedious process. You have to calculate each one of these by hand. So what we're going to look at next is a similar approach, but a slightly different notation. So we want point Q to be close to the original point P. That way we're going to get a better approximation. So instead of just randomly picking a point Q, we're going to define our point Q to be starting at 1 plus some delta x distance away. So if you visualize that graph again of our function, which was our upside down parabola like this, point P was right when x was 1. So now what we're going to do is we're going to let Q start at 1 and just go some little distance delta x away. So 1 plus delta x might be over here, or if delta x was something negative, it could be something on this side as well. So our point Q is just a little distance away from P. And typically we want this delta x to be really small so that our point Q and our point P are really close together. So we're just adding a little tiny bit of distance between our 2 points. Okay? And then the y value of this point Q would just be whatever you get when you plug in 1 plus delta x into our formula. So here's our chart that we are going to fill out. These distances here are what delta x needs to be, and what we want to figure out is what Q is going to have for its coordinates, and then based on that figure out what its slope is. So for example, if I say that delta x is 0.1, then that means point Q is actually going to have as its x coordinate 1 plus 0.1. So that would be 1.1. So our point Q is pretty close to P. It's at 1.1. Now how would you find that y coordinate? Well, we could go back to our equation up here, negative 16x squared plus 16x plus 32, and substitute in 1.1 in for these x's. Okay, and you can do that on your calculator. I'm going to show you in a minute how to do it using some tables so that you can make the calculator do a lot of the calculations for you fairly efficiently and quickly. But before I show you that on the calculator, I just want to convince you or show you what these actual values over here represent, these delta x's. So if delta x is 0.1, that's letting Q have an x value of 1.1. If I let delta x be 0.01, then that means we're letting the x value of Q be 1.01. If I let delta x be 0.001, then I'm really looking at 1.001 for the x value, and finally 1.001 for the x value of our last point Q. So you can see that as these delta x's get smaller, these Q values are getting closer and closer to 1, which means point Q is getting closer and closer to point P. And that's what we want. The closer we get our point Q to point P, the better our approximation of these slopes is going to be. Now, to plug each of these into that quadratic function to find the y's is pretty tedious. And then from there, we'd have to do our different change in y's over change in x's, which is also pretty tedious. So the first thing I'm going to do on my calculator is figure out what all of these y values are going to be. And I'm going to use my list command on my calculator to help me do that. So already in my calculator, in list 1, I have those delta x values typed in, 0.1, 0.01, 0.001, and then 1 times 10 to the negative 4 is the same as 0.0001. Now what I want to do in list 2 is figure out what the y values are going to be. And that means we don't want to be substituting in these list 1 values into our function. We actually want to be substituting in these list 1 values plus 1. Because remember, Q has as its x value not 0.1, but 1.1. And Q has as its x value not 0.01, but 1.01. So when we type in our function down here for list 2, I'm not going to be typing in for x these list 1 values. I'm actually going to be using for x these list 1 values plus a 1, so that we are this distance away from our point P. So if we do this, here's what we're going to have to type in carefully. So the equation of our function is negative 16x squared to begin with. So I'm going to type in negative 16, but instead of x, we want 1 plus delta x, and these delta x's are stored in list 1. So I'm going to type in 1 plus list 1 quantity squared. So that's the x value that I'm actually using, 1 plus our delta x's, which are stored in these list 1's. Then my function was a plus 16x. Now again, I don't want to use x, I want to use 1 plus my delta x's, and the delta x's are stored in list 1. And then finally on the end was plus 32. So if I hit enter, these are what So the first one was 30.24, and then we had 31.838, 31.984, and 31.998. And these are the y coordinates of our point Q's. Now, one thing you should be noticing, and we said this earlier, as these delta x's get smaller and smaller, the point Q's should be getting closer and closer to P. And remember what the y value of point P was. It was 1,32. So these y values of our point Q should also be getting closer and closer to 32, and it appears that they are. So we're doing things right so far. Now once we know our x and our y coordinates of our point Q, and we know that P is 1,32, all we need to do now is find our slopes. And to find our slopes between these 2 points, remember that it's just the y value of our point Q, so whatever these y values are here, minus the y value of point P, which is 32, divided by the difference in the x's. So the x value of point Q is 1 plus delta x, and the x value of point P was just 1. Now if you notice down here in the denominator, these 2 1's are going to cancel. So just to simplify our formula here a little bit, our slope of our secant lines are going to be this f of 1 plus delta x, which again are all these y coordinates of whatever our point Q is that we're looking at, minus 32, the y coordinate of point P, over just our delta x. So again, I'm going to use my calculator to calculate this for me in my list 3. And to do this correctly and type it in correctly, we're going to be referring to these f of 1 plus delta x's. And remember what those were. That if this was list 1 on my calculator, list 2 was exactly those f of 1 plus delta x's, those y coordinates of our point Q. So this formula right here is really whatever number I have in list 2, these y values right here, minus 32, which is the y value of point P, over my delta x's. And where are the delta x's stored in my list? My delta x's are stored in list 1. So this is the formula I'm going to type into my calculator into list 3 so that I can make the calculator compute all of these slopes really, really quickly. So if I pull up my calculator, I'm going to arrow over to the top of list 3, and I'm going to calculate my slopes. So my slopes are the y's subtracted, and the y's of point Q are right here in list 2. So I want to do parentheses, list 2, minus the y coordinate of point P, which we knew was 32. So there's the difference in my y's. And then I want to divide this by the difference in the x's. And since the P and the point Q are only a distance of delta x apart, then in the bottom what we're really just dividing by are my delta x's. And the delta x's are stored in list 1. So I'm going to type in list 1 on the bottom. Make sure you're using parentheses around that numerator. So if I hit enter, then these values in list 3 represent the slopes of my secant lines as point Q gets closer and closer to point P. So let's copy these down. So the first slope was negative 17.6. The next slope, as I got a little bit closer, was negative 16.16. And then the next slope was negative 16.02. And as I got really, really close, the slope was negative 16. So what does this represent for us? It means the closer that Q gets to P, the closer the secant slopes get to the tangent line slope. So what would be a good guess as to what the true tangent line slope would be? What are these values here approaching as these delta x's get smaller? It looks like they're getting closer and closer to -16. So a good guess would be that the tangent line slope is probably -16. And what is it called in calculus when you get closer and closer to something? That's called a limit. So we are going to use limits to represent how to calculate a tangent line slope. Now, one comment before I move on here. If the whole calculator stuff with the list 1 and the list 2 confuses you, then feel free to do these by hand. I'm just trying to show you a way of using the technology to help calculate some of these fairly efficiently. But if it's too confusing, then just take your delta x's, add 1 to them, plug it into your formula for f of x to find these y's, and then just do your y2 minus y1 over x2 minus x1. And you can compute all of these by hand if you want to. So instead of using specific numbers for point Q, we're going to try to generalize our idea here. We're going to try to find the slope in general and find it symbolically. So let's show what our 2 points are again. Remember, point P was 1, 32. And that 32 is what you get when you plug in 1 into your function. So 32 is really f of 1. Point Q in general is 1 plus some little distance away, so 1 plus delta x, and the y value of point Q is whatever you get when you plug in 1 plus delta x into your function. So these are our 2 points, and how do you find the slope between these 2 points? You take the y2 minus the y1, and that's what I have right here in the numerator, over the x2 minus the x1, and that's what I have in the denominator. So let's go ahead and use our actual function, which was -16x squared plus 16x plus 32, and let's actually calculate some of these things. Now in the denominator, we already noticed this on the previous page, these 1's cancel out. So the denominator is just going to clean up into a delta x. Now in the numerator, we're going to do this symbolically. We're not going to have an actual number to plug in for x. Instead, what I want to plug in is this whole expression 1 plus delta x. And what you want to think of there is this is really the function f of stuff. So this rule for f says to take -16 times that stuff squared plus 16 times that stuff plus 32. And what I'm going to be plugging in for my stuff is this 1 plus delta x. So you need to put it in both of these 2 positions, and I'm going to wrap it in parentheses because I have some constants out front and some powers to worry about. So the correct expression for f of 1 plus delta x is -16 parentheses 1 plus delta x squared plus 16 parentheses 1 plus delta x plus 32. Now that's just this part. We want to subtract from that f of 1. And you can either plug in 1 for x, or you can just remember that f of 1 is this 32. So you'll get 32 regardless of how you do it. So this is what I mean by doing it symbolically. We're not actually plugging in decimals like 1.001 into our function. We're plugging in symbols, 1 plus delta x, and we're going to see what this simplifies to. Now one quick thing you should notice on top are these 32's. They're going to cancel out. Now to simplify the rest of this, we are going to need to square this quantity right here, and we're going to need to distribute our 16's across. Now as a little side note, we are going to need to square this 1 plus delta x quantity. So you can either think of that as 1 plus delta x times 1 plus delta x and then just FOIL, or hopefully you're familiar enough by now to do that in your head. You know that you're going to get a 1 times a 1, you're going to get a delta x plus another delta x, which is 2 delta x, and then we're going to get a delta x times a delta x, which is a delta x squared. So we are going to have to take negative 16 times these three terms. This is what we get when we square that quantity. So in my next step, let's go ahead and distribute those 16s across. This first one is actually a negative. So we're going to get a negative 16 minus 32 delta x minus 16 delta x squared. And then here we're going to get plus 16 delta x. So let's see what cancels. Our 16 and our negative 16 cancel out. And what we're left with in the numerator here has terms with delta x's. We have a delta x here, here, and here. So since they all have a delta x, I can factor it out just like a GCF. And that would leave me with this negative 32 minus, if I take one of these delta x's away, I still have one left, plus that minus 16 in front. And if I take this delta x away, I'm just left with a 16. Finally, on the top and the bottom, these delta x's match so they can cancel out. And so what we're left with is negative 32 minus 16 delta x plus 16, and we have a couple of like terms there. Negative 32 plus 16 is a negative 16 minus that 16 delta x. So our final answer is negative 16 minus 16 delta x. And what did we just find? What was the whole purpose of this? This is finding a symbolic representation of what the slope between P and Q equals. So this is the secant slope, secant line slope between point P and point Q, and it's going to have as its formula negative 16 minus 16 delta x. So if you tell me that point Q is 0.1 away from point P, then I could just plug in 0.1 for this delta x, and that would tell me what the secant slope would be. And I wouldn't have to go through all the work of making those tables like I did on the last page to figure it out. I could just plug in that delta x very, very quickly. So it's a real time saver to do all of this calculation once, and then you could go back to your table over here and plug in each of these delta x values into this formula, and it's a much simpler calculation to get that final slope. Okay? Now, what is the purpose of these secant line slopes? Well, remember our idea here is that we're taking these point Q's and we're letting this delta x get smaller and smaller and smaller so that point Q gets closer to point P. And if we do that, then in the limit, that slope of this secant line should turn into the slope of our tangent line. So let's go ahead and formalize that in a limit statement. So here, right here, represents that secant line slope, the difference in the two y values, point Q's y minus point P's y, over that delta x. And what we're doing is we're letting this delta x go to 0. And the smaller that delta x gets, that means point Q is getting closer to point P. So what does this turn into when we do that limit? Well, in this particular example, this whole quotient that we got right here simplified to this formula. So in the limit, if I plug in 0 for that delta x, then this is just going to go to negative 16. And that was what we saw earlier from our table of values. We were pretty sure, pretty confident that negative 16 was going to be what that limit was. So here we just did it algebraically instead of doing it numerically. And what's the significance of this negative 16? When you take the limit as delta x goes to 0, this answer becomes the slope of the tangent line. Okay? So this limit is the number that we assign to the slope of the tangent line to the curve at the point 1, 32. So in general, to find the slope of a secant line from any point c, f of c to a point c plus delta x, f of c plus delta x. So this is like our point P, and this is like our point Q. The slope between those 2 points would be this y value minus this y value. So f of c plus delta x minus f of c over this x minus this x, which is just going to give you that delta x in the bottom. So that's the slope of our secant line. And that also has another name. It's called the average rate of change of y with respect to x. So the average rate of change is just this secant line slope. Okay, those change in y's over those change in x's. In this example, the slope of each secant line that we calculated was just an estimate of the slope of the tangent line at the point c, f of c. To find the actual slope of the tangent line, we have to take the limit as delta x approaches 0 in this expression. So to get the tangent line slope, you have to take the limit as delta x goes to 0 of these y's over these x's, changes in y's over changes in x's. And this, by the way, is called an instantaneous rate of change. Okay? Now, I'm going to show you a quick little animation here that will help you visualize how these secant lines approximate these tangent lines. So here is just a random graph, and this red dot would be our point P. So if I click anywhere on this graph, now I've created a second point Q. So this red line that you see right here represents the secant line between point P and point Q. Now as I drag this point closer and closer to point P, you can see how these secant lines are changing. And if I can drag that point right over point P, now it turns blue, and that's the actual tangent line itself. So the red lines, whether I go to the right or to the left, these are all secant lines. The further away I get, the worse the approximation is going to be to what that blue line looked like. So here's that blue tangent line. Oops. And we want to be as close to it as we can. And the farther away we get, those secant lines get farther and farther away. The closer we get, the closer those secant lines look to our tangent lines. Okay. Formalize this into a definition. So the definition of a tangent line with slope m. If f is defined on an open interval containing c, and if the limit as delta x goes to 0 of these delta y's over delta x's, or in other words, the change in the y's over the change in the x's, goes to m. So if this limit exists and has a value of m, then the line passing through c, f of c with slope m is called the tangent line to the graph of f at the point c, f of c. So this is that blue line that we were just talking about. Note that the slope of the tangent line at c, f of c is sometimes just called the slope of the graph of f at c. When you take the limit as delta x goes to 0, That's what turns this into the tangent line slope. And that's also what turns it into something called the instantaneous rate of change. If you don't have that limit out front and you just have this difference quotient right here, that's called an average rate of change. So the average rate of change are these secant line slopes. But as soon as you take the limit, then those secant line slopes turn into your tangent line slope. So the instantaneous rate of change uses the limit as delta x goes to 0 to get the tangent line slope. Whereas the average rate of change does not use the limit and just gets you the secant line slopes. It's a lot of terminology to get used to. This is a tough lecture, so give yourself some time to absorb all of this information and kind of just digest it so that it can sink in a little bit. So a note regarding the slope formula. M equals the limit as delta x goes to 0 of f of c plus delta x minus f of c all over delta x. That's our tangent line slope right there, okay? As soon as you take those secant slopes, which are these right here, and you put a limit in front of that, as delta x gets smaller and smaller, you're turning it into your tangent line slope. So in this notation right here, the point c comma f of c is the point at which you are trying to find a tangent line. So in our first example, that was that 1 comma 32. So the c would be the 1, and the f of c would be the 32. Okay? Now, an alternative way to think of this is instead of using a specific point, c comma f of c, we could just use a general point, x comma f of x. So instead of putting c's in right here and right here, we can just replace them with a general x and calculate this slope formula. So an alternative is to think of this formula m using x's, where we generally find a slope formula for a given curve, which can be used to find the slope at any point x on the curve rather than at a specific point c. And this alternative is equally easy to use, and it's probably a bit more useful. We just simplify this expression for the given function, and then at the end, after we've simplified, then we plug in our desired point. So this is typically how we're going to do it, and I'm going to show you lots of examples, but usually we find a slope formula that calculates the tangent line slope at any point x. And then if you really want to know the tangent line slope at a specific point, then you just plug in that x value at the end after you've simplified. So let's see an example. Find the equation of the tangent line to the curve f of x equals x cubed plus x squared at the point 1 comma 2. We will do this problem using both the specific, which is the one with the c's, and the more general, which is the one with the x's, slope formula. So we're going to do both ways so you can compare and contrast. After finding the equation, we're going to sketch the graph of the curve with our tangent line on our calculator and try to visualize what's going on. Alright, so our function f of x is x cubed plus x squared, and we're trying to find the equation of the tangent line to this curve at the point 1 comma 2. So there's two ways to do this. You can do it at a specific point, and in this problem, our point is 1 comma 2, so the c would be 1, and the f of c would be the 2. Or you can do it in a more general way, where you're doing it at any point x comma f of x, and then we're going to plug in x equals to 1, which is our point that we want to look at the end. So we're not going to use our point 1 comma 2 until the very end when we do it in the general way. So let's start with our specific method. This is how we've done it so far. So this is a formula that you want to memorize. This, by definition, is the slope of the tangent line. So to find this slope, you need to find the limit, as delta x goes to 0, of the difference in these y values over the difference in the x's, which is just that delta x. So we need to find f of c plus delta x, and in our specific method, we're actually going to use c equals to 1. So I'm going to plug in 1 plus delta x minus f of c, or f of 1, all over delta x. So we're actually using a number for that c. So now if we plug in what we know, we want to figure out what f of 1 plus delta x is. Now to figure that out symbolically, we have to use our function rule up here. And this is really like f of stuff equals stuff cubed plus stuff squared. And what I want for my stuff right here is 1 plus delta x. So I need to do that 1 plus delta x cubed plus that 1 plus delta x squared. So all I did was I plugged in my input right into those two boxes. So that is what f of 1 plus delta x gives us. We want to subtract from that f of 1. So now we're going to plug in 1 into these boxes. 1 cubed plus 1 squared is just 2. And we already knew that because we knew that the point went through 1 comma 2. So now we've plugged in our function and our input values. And the rest of this is just going to be some algebra. Now in a few other previous lectures we've done this before, so I'm not going to go through it all out. But to figure out 1 plus delta x quantity cubed, you can do it the long way, which would be to FOIL this out, or you can just memorize the formula for how to cube a sum. It's the first term cubed, 1 cubed stays 1, then you have a middle term, and then it's going to be 3 times delta x plus 3 times delta x squared plus delta x cubed. And then in the middle, we want to square our binomial. So if we FOIL that out, or do it in your head, you're going to get a 1 squared, you're going to get 2 delta x's, and then you're going to get a delta x squared on the end. And then we have our minus 2 on the side, and all of this is over our delta x. Now some things should cancel here. Our 1 plus 1 is 2, and that's going to cancel our minus 2. And if we look for some like terms here, I have a 3 delta x and a 2 delta x, which is a 5 delta x. And I have a 3 delta x squared plus another delta x squared, which is 4 delta x squared. And then I have that delta x cubed. Now because all of those terms in the numerator have a delta x, that's good news, because that means we can factor out that delta x from the top, just like a GCF, and in parentheses I would be left with 5 plus 4 delta x plus delta x squared, and the delta x's on the top and the bottom cancel, which should always be your next to last step, because now at this point what you're left with should be something that you can now plug in for. And we're going to be plugging in 0 for these two delta x's. So this will go to 0 and this will go to 0, leaving me just 5. And what did we just figure out? What is this 5? This is the slope of the tangent line. Okay, so this is going to be what we call m. All right. Now, we're not quite done with this problem because it actually wanted us to find the equation of the tangent line, but before I get to that, let's go back up here and let's contrast this method that we just did using a c value of 1 with the more general way of doing this. So on this second approach, what we're going to be doing is not plugging in a specific c, we're just going to leave x's and delta x's in our formula. But it's going to look very, very similar to what we just did. So in this method, we are going to be plugging in x plus delta x into our function. and then subtract from that f of x over delta x. So instead of plugging in to our boxes up here 1 plus delta x, now I'm plugging into my box x plus delta x here and here. So when I use my function rule, this is going to become x plus delta x quantity cubed plus x plus delta x quantity squared. That's from my function. And then I'm subtracting from that f of x. So this time I'm plugging in just an x into these boxes. So this would become just normal old rule, x cubed plus x squared. Now be careful here. You want to subtract all of f of x from all of f of x plus delta x. So you must have parentheses to subtract both of these terms from these two terms on top. And we're going to need those parentheses because we are going to have to distribute our negative across. Now in the next step here, the rest of this is just a bunch of simplifying. And you can see that it's very, very similar to the algebra and arithmetic that we did on the previous problem. But this time we don't have ones, we have x's. So when I cube x plus delta x quantity cubed, that's going to give me an x cubed plus a 3x squared delta x plus a 3x delta x squared plus a delta x cubed. I'm also going to get, when I square x plus delta x, an x squared plus a 2x delta x plus a delta x squared. And then when I distribute my negative across, I have a minus x cubed and a minus x squared, and all of that is over my delta x. And ideally, some terms should cancel. My x cubes cancel, and my x squareds cancel, and we have a few like terms as well. So let's see how we can simplify this. We have, actually, it looks like we don't have any like terms. I misspoke. So we have a 3x squared delta x plus a 3x delta x squared plus a delta x cubed plus a 2x delta x plus a delta x squared. Now you are in good shape if every single one of those has a delta x in it. And they all do, because now what we're going to do is pull it out, factor it out. And that's going to leave me with a 3x squared plus a 3x delta x plus a delta x squared plus a 2x plus a delta x. And that delta x that we just pulled out cancels with the one on the bottom. And once you do that canceling step, you're ready to plug in 0 for just the delta x quantity. Don't plug it in for x, just plug it in for delta x. So this becomes a 0, this becomes a 0, this becomes a 0. And that means what we're left with is the 3x squared, this whole term goes away, this term goes away, this term goes away, plus 2x. Notice the difference between our two final answers. This one gives us a formula still involving x, and we're not quite done yet. What this represents is the slope of the tangent line at any point x. And we want the slope when x is 1. So what we're going to do now, what the major difference between these two approaches is, in this second approach, you leave in your x's, and then at the very end, you're going to plug in and let your x be the specific point you want to look at. We wanted to let x be 1. So if I plug in 1, I'm going to get 3 times 1 squared plus 2 times 1, and that's just 5. So we still end up with exactly the same slope that we got over here. We just had to plug in 1 at the very end. The reason we do this more general approach is because several times, or several kinds of problems, might ask you to find the slope at many different points. So you wouldn't have to recalculate this red approach for each of the different C's. Instead, you could just do it once and then plug in your different C's at the very end. So it saves you on the amount of time you have to spend doing the algebra. So we got the same slope, but we're not quite done with answering the final question here. The final question wanted to know what the equation of the tangent line is. So you're not done yet. How do you find the equation of any line? Well, you need a slope, which thankfully we just figured out was 5, and you need a point. And we know the point because the point that we were being told to look at was this 1, 2. So once we have our slope of 5 and our point 1, 2, all I have to do at this point is use my point slope form to figure out the equation of my line. And this is this form down here that you should have memorized. So to figure out the equation of our line, we're just going to do y minus our y coordinate, which was 2, equals our slope, which we calculated to be 5, parentheses, x minus our x coordinate, which is 1. And then we just have to clean this up. So we get y minus 2 equals 5x minus 5, and when I add 2 to both sides, we get y equals 5x minus 3. So this is our tangent line right here. This is the equation of our tangent line. So one last thing on this problem before we move on. We're going to take a look at our calculator to see what this represents or what this looks like so we can visualize everything that we've been talking about so far. So on my calculator, I have typed into my y1 the equation of our curve, which was that x cubed plus x squared. And then in y2, I've gone ahead and typed in my equation of the tangent line that we came up with, which was y equals 5x minus 3. So let's start with just a zoom standard. And what we should see is our cubic function, and then we should see that tangent line. Now what we're going to do is we're going to go ahead and try and see what happens as we look a little bit closer at our point in question, which was that 1, 2. So let's go ahead and hit trace. And one nice feature on a graphing calculator, I don't know if you know this or not, is that you can just type in the actual x value that you want to jump immediately to. So if I hit 1, then it's going to jump right to the point x, 1, y, 2 on my cubic function. And what I'm going to do is I'm just going to zoom in on my graph right at that point. So let's go to zoom, and I'm going to do a zoom in number 2, and I'm going to hit enter. And it's just going to zoom in on my graph so we can see a little bit more closely. Now you can see that my tangent line does seem to look pretty good. And what I want to do again is I'm going to zoom in closer yet and see what's going on. So let's hit trace and hit number 1 again so I can get right on that point 1, 2 that I'm interested in. And let's do another zoom in again. Hit enter. There's my cubic. And there's my tangent line. Can you see how close together they are? That's a good thing. That means that the closer or the more I zoom in on my function, my cubic function, the more and more it looks like my tangent line. And that's what a tangent line is supposed to be. It's supposed to be a linear approximation to your curve. And the closer you zoom in, the more linear your graph should become. And it should line up exactly with that tangent line if you found your tangent line correctly. So let's try this one more time. Trace at 1, 2, and I'm going to zoom in one more time. And what I want to see is really no difference between my curve, my function, and my tangent line. And here you can see that they graphed right on top of each other, which means the tangent line that we came up with is a really, really, really good fit for our function right around the point 1, 2. Now this property of a function being able to zoom in on it enough times so that it eventually becomes linear is something called being locally linear, and that's a good property for our functions to have because that means they will have tangent lines and tangent line slopes. Okay? Alright, let's go ahead and move on to the next question. Okay, in our next example, we want to find the equation of a tangent line to the curve f of x equals 1 over the square root of x at the point 4, 1/2. Now, if you want to know the equation of a tangent line, you have to know the slope of the tangent line. And the slope of the tangent line is going to be given by our limit definition right here. So that's always going to be the first place you start. So we're going to start with our limit definition of our slope. and we're going to substitute in x plus delta x in for our input, and then we're going to substitute in x for our input and then start cleaning that up. So let's start by taking f of x plus delta x. So this is my new input, and it's going to go right where that input variable is supposed to be. So when I substitute in x plus delta x, this function should become 1 over square root of x plus delta x. And then I'm going to substitute in just x for this second function part, and that would just give me 1 over square root of x, and we want to subtract both of those. So here's what we have when we substitute in our function, and now at this point we're going to need to clean this up. If I try to plug in 0 right away, this delta x would go to 0, and I'd get 1 over square root of x minus 1 over square root of x, which is a 0, and the bottom goes to 0 as well, so we'd be getting one of those indeterminate forms. So we can't just substitute in right away. We're going to have to be a little bit clever and try to manipulate this. Now, because there are fractions involved, a good strategy when we're trying to evaluate limits that have fractions, complex fractions that is to multiply by a common denominator. So I have this factor right here in one denominator and square root of x in the other denominator, so my common denominator would require both of those. So what I'm going to do is I'm going to multiply on the top and on the bottom by these two denominators multiplied together, my common denominator. So square root of x plus delta x times square root of x. And I'm doing that to the top and to the bottom so that I keep the fraction balanced and I'm not changing the original problem. I'm just going to write it in a different form. So what happens if we multiply this first fraction times my common denominator? Well, the square root of x plus delta x is canceled out, and I'm left with 1 times square root of x, which is just square root of x. When I go and I multiply my second fraction times my common denominator, this time the square root of x is canceled out, so I'm left with 1 times this square root of x plus delta x. So we'll have a minus square root of x plus delta x left over. In the denominator, we just have 3 different things being multiplied, and the denominator does not have a bottom to its fraction. There's nothing underneath this delta x to cancel either of these two guys out. So we're going to have all 3 left over. It doesn't matter in what order you multiply them in. You just want to recopy all 3. Now, at this point, if we tried to plug in 0, we'd still get 0 over 0, because this delta x would go to 0, making me have square root of x minus square root of x on top, which is 0, and then the bottom is being multiplied by this delta x, which is going to 0, so that would also give me 0 over 0. So right now, we're still kind of stuck, and we haven't been able to make too much progress. However, we have gotten rid of our fractions on top. So at this point, if you look at what's left, since we've gotten rid of our fractions, we still have some radicals. And when you have that indeterminate form, 0 over 0, a good strategy to use when there's radicals involved is multiplying by a conjugate. So this problem actually requires doing a couple of different strategies. So what I'm going to do is I'm going to multiply again on the top and the bottom, but this time what I'm going to multiply by is the conjugate of this numerator. So the conjugate will be exactly this same expression, but instead of having a minus in between, I'll have a plus. So it's the same expression but with the opposite sign in between. So that would be square root of x plus square root of x plus delta x. And we have to multiply by that on the bottom as well to keep my original problem equivalent. I'm going to use some parentheses here to help remind me that I need to do some foiling. And if I go ahead and I distribute across the top, notice that because we're using a conjugate where we have opposite signs, that creates a difference of squares pattern. So the inner and the outer terms will always cancel out because one will be minus and one will be plus. So the only terms that are going to make a difference are the first times the first, and square root of x times square root of x is just x. And then the last times the last. Square root of x plus delta x times itself is just x plus delta x without the square root. It's going to be a minus because you have a minus times a plus, but be careful here. We don't want to just put our minus like that. We want minus this whole quantity since all of that quantity was under my radical. In the denominator, you don't want to distribute. We're just going to recopy these 4 different factors. You don't want to distribute because you're going to need it undistributed so that we can eventually cancel out that delta x in the bottom. So I'm just recopying everything that I had in that denominator. Now when we distribute across the top this negative, you can see that these x's are going to cancel. We'll have an x minus an x, but we'll have left over that negative as well as that delta x on top. And that delta x is good because that's the delta x that we need on top to cancel out the delta x that's giving us our 0 in the bottom. So once we get to this point, we can then cancel out our delta x's. And remember that that is usually the indicator that you're ready to plug in once you've canceled out those delta x's. On top we have a negative 1. On the bottom we have x plus delta x under that radical, square root of x, and then parentheses square root of x plus square root of x plus delta x. So we're ready to plug in, and what we're plugging in is 0 for these delta x's. So this goes to 0 and this goes to 0. You're not plugging in anything for the x's. Remember that when you use this general limit definition for the slope of the tangent line, what you're going to end up with is a formula involving x's. So it's okay to have x's still in your answer. So let's see what this is going to give me. I have that negative 1 on top. I have this square root of x from right here. I have a square root of x from in the middle, and then in these parentheses I have a square root of x plus another square root of x. So the square root of x times square root of x that I have out front of my parentheses just becomes an x, and square root of x plus square root of x, that's like an apple plus an apple gives me 2 apples, so this is going to give me 2 square root of x. And if you just want to make it a tiny bit neater, you don't have to do this, but you could put that 2 out front and make it negative 1 over 2x root x. You could even rationalize that denominator by multiplying the top and the bottom by square root of x. That's totally up to you. So this is what we call our slope function. This is our tangent line slope at any x. And keep in mind, in the original problem, we wanted the slope at this particular point, so when the x is 4. So what we're going to do at this point is once we have done all the work to come up with our slope function, now we're going to plug in x equals to 4 into this slope formula. So at x equals to 4, this slope m becomes negative 1 over 2 times 4 times the square root of 4, which is negative 1 over 8 times 2, or negative 1/16. And then last but not least, so there's your slope m. We have our point 4, 1/2. Last but not least is to put these two things together into the equation of our tangent line. So remember that to find the equation of your tangent line, you're going to need to use that point slope formula. Y minus the y coordinate, which in this problem is this 1/2, equals our slope, which we just worked really hard to find, negative 1/16, times x minus the x coordinate, which is our 4. And then you just want to clean that up a little bit. So we're going to get y minus 1/2 equals negative 1/16 x. A negative times a negative is a positive, and 4 times 1/16 is 1/4. If I add a half to both sides, then we get y equals negative 1/16 x plus 3/4. So this is the equation of our tangent line. And what you should do, if you had a graph of this on your calculator, what you should be able to see is that this curve, this function, 1 over root x, if you were to zoom in on it at 4, 1/2, then the curve should start to look exactly like the equation of this line right here. And the more you zoom in, the more that curve turns linear and matches right up with this tangent line, because that's what your tangent line is doing. It's approximating your curve and finding the best linear function that sort of fits the direction of the curve. Okay? All right, next thing we're going to do is learn a little bit of vocabulary that goes along with this limit definition of the slope of a tangent line. So the limit used to define the slope of a tangent line is also used to define one of the 2 fundamental operations of calculus called differentiation. There's 2 major branches of calculus. Differentiation is one, that's what we're going to talk about today, and the other branch is called integral calculus, and we'll get to that eventually. So differentiation is based on something called the derivative, and it turns out that the definition of the derivative is exactly this limit definition of the slope of the tangent line that we just came up with. So this limit right here that we have already used several times is now going to be called the derivative of f at x. And the notation that we're going to use for that most often is this f with that little mark called a prime up there. So this would be pronounced f prime of x, and that's defined to be the derivative of the function at x, and it represents the slope of the tangent line to that function at x as well. Now, because this is a limit, not all limits exist, so sometimes there may not be a derivative if this limit doesn't exist. So this is going to be called the derivative for all x values for which this limit exists. Now, this means that the derivative of f of x gives the slope of the tangent line to the graph of f at the point x, f of x, provided there is a tangent line at this point. So the derivative is now the same exact thing as the slope of the tangent line. The process of finding the derivative, that's called differentiation. And we say that a function is differentiable at x if its derivative exists at x, and it's differentiable on an open interval if it's differentiable at every point on that interval. Now we're going to see several different notations for the derivative. One of the most common is that f prime notation, so f prime of x. You could also see that written as y prime if you're talking about your function in terms of y's and x's instead of f's and x's. So if you're not using f but you're calling it y, it would be called y prime. So those are equivalent. Now you might see this notation as well, and this is pretty common, dy over dx or df over dx, or dx of the function. This could also be written as df over dx as well. So those are more common as well. I'll talk about those a little bit more in just a second. This last notation over here is a lot less common. You see this great big D, which is like a differentiation operator, and it's taking the derivative of this y with respect to that little x at the bottom. So this means the derivative of y with respect to x. Okay? So why do you see sometimes this dy over dx notation? Well, it comes from the fact that the way that we've defined a derivative is that it's a slope, right? And how do you find slopes? You find slopes by doing change in y over change in x. And how do we turn those secant slopes into tangent slopes? We take a limit. We take the limit as delta x goes to 0. So when you take that limit, as those delta x's go to 0, these little triangles turn into these little d's. Okay, so the secant slopes turn into the tangent slopes as soon as you take that limit. So that's where that dy over dx notation comes from. It's really coming from that change in y, which is the Greek letter delta, d, over the change in x. Okay? And again, if you're using f notation instead of y notation, then this would be the same as df dx. Okay, so you can see those interchangeably. And I will ask for problems using all of these different notations, so you'll want to be familiar with all of them. So here's our steps for finding a derivative. First thing you're going to do is write down that difference quotient, that f of x plus delta x minus f of x all over delta x, and then you're going to simplify that, and then you're going to take the limit of that as delta x goes to 0. So essentially what we're finding when we're asking to find the derivative f prime of x is you're taking the limit as delta x goes to 0 of this difference quotient, these slopes, changes in y's over changes in x's. So this is the formula that you want to have memorized. So let's take a peek at a couple of examples here. We want to find the derivative f prime of x for each of the functions below. So a couple of things to notice here. It says find the derivative f prime of x. So that means find that limit definition, what we have right up here. Find this. Okay, that's what that means when it says find the derivative. Find this limit of this difference quotient. Notice that this is not asking for the derivative at a specific point. So unlike the last example we did where we plugged in 4 for x, we're not going to do that here. We're just going to find this limit and we'll simplify it and come up with a final answer, and that final answer will be a function of x. It might still have some x's in its final answer, and that's okay. We're finding this derivative function. So this represents the slope of our tangent line at any x. So in these problems, we're not plugging in anything for x. Okay, we're just going to simplify and then be done. So let's start with something relatively straightforward, a nice straight line. This is a linear function, negative 2x plus 5. So if I want to find the derivative f prime of x, here's the formula that you're going to use, and you want to have this memorized. The derivative is defined to be, this is called its limit definition. The limit definition of the derivative is that the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. That is what your derivative is. So we're going to apply this to our particular function. So we're going to be taking the limit as delta x goes to 0 of f of x plus delta x. So by now we should know what to do with that. We're going to take this input and we're going to substitute it in for that input variable. So this becomes negative 2 parentheses, not just x, but x plus delta x. And then that plus 5 is on the side. So all I did is I replaced that x with this new input. Now I'm going to do that again, but this time I'm going to substitute in just plain old x for that x. So that would be negative 2x plus 5. Now be careful here, we're subtracting these two f's. So we want to subtract these two results, which means I need to subtract all of this from all of this. So it's important to have parentheses around that f of x, because you will need to distribute that negative. And that's what we're going to do in our next step here. We're going to do all of our distributing to help simplify this difference quotient. So let's distribute our negative 2 across, negative 2x minus 2 delta x plus 5. And if I distribute my negative here, this becomes a positive 2x and a minus 5. And luckily, the negative 2x and the positive 2x cancel, the 5 and the minus 5 cancel, and what I'm left with on the top is just that negative 2 delta x over delta x. Those delta x's cancel, and that just gives me the limit as delta x goes to 0 of negative 2. So at this point, after we've canceled those delta x's, usually this is the point where we substitute in 0 for our delta x's, but there aren't any delta x's left. This is just the limit of a constant, and the limit of a constant is that constant right back again. So what we've just found out is that the derivative function is -2. Now what does that mean? It means that the slope of the tangent line to this function up here will always be -2. And that should make sense geometrically, because this line right here has a y-intercept of 5 and it has a slope of -2, so it's going to come down like that. So visualize what these little tangent lines would look like. If I looked at this point, my tangent line is going to look exactly like the line itself, because a tangent line to a line is the line itself. And what is the slope of all of these little tangent lines? Well, they're going to be the same as the slope of this line itself, which we know is -2. So it makes sense that the derivative at any point that we look at would be -2, since the slope of this line at any point we look at is -2. So you probably could have come up with that answer without having to do any of this work. Okay, let's hope. All right, let's try another one. So this time we want to find the derivative of the function 7x squared. Okay, so your starting point is always going to be to use our limit definition of the derivative, which is f prime of x is defined to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And what we're going to do is we're going to substitute into our function. So we're going to substitute in x plus delta x right here for that x. So this becomes 7 parentheses x plus delta x squared. Then we're going to subtract from that x plugged in, which would just be 7x squared. Now we have a little bit of algebra to do on that to clean it up. You want to simplify your difference quotient first before you take the limit. So if I were to take x plus delta x and square that quantity, that would become an x squared plus a 2 delta x times an x plus a delta x squared. And we want to take all of that times 7. So now at this point, I'm going to distribute that 7 across, and that's going to give me 7x squared plus 14 times delta x times x plus 7 delta x squared minus 7x squared. Those 7x squareds cancel, and in the numerator, what I'm going to be left with are terms that only have delta x's. I have one here and I have some here. So if I factor out that delta x, then this term would be left with a 14x, and this term would be left with a 7 delta x. Once I've factored out my delta x, they cancel, and what I'm left with is now something that I can plug in 0 to for my delta x. Remember, the 0 is going where that delta x is only, so this whole term will go to 0, which means my final answer is just 14x. So my derivative function is 14x. And this is not a constant because this is a parabola that we started with. So as you move and progress around your curve, those tangent line slopes are going to change. And this is the function that determines what the slope is at any value of x. So you give me an x, you give me a point, and I can tell you exactly what the slope of the tangent line is at that point by just plugging in x. That's what this derivative does for us. Alright, let's try a couple more that are a little bit more complicated. These are both involving some fractions. So we want to find the derivative of the function 1 over 1 minus x. So we always start with our limit definition of the derivative. F prime of x, the derivative, is defined to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So I start by plugging in x plus delta x right where that input variable is supposed to be. Use parentheses around it because there's a minus in front of that x. So this is going to be 1 over 1 minus x plus delta x wrapped in parentheses. Then I'm going to subtract from that just with an x plugged in. So that will stay 1 over 1 minus x. Now we did one like this earlier where we had these complex fractions. So the trick to simplifying these is to multiply by the common denominator, which would be this denominator times this denominator. So I'm going to multiply by both on the top and on the bottom. So in the numerator, when I multiply this first fraction across, this will cancel out over here, leaving me with 1 times 1 minus x, or just 1 minus x. Then I'm going to subtract from that. When I multiply this second fraction, this time the 1 minus x's cancel, so I'm left with this other factor, the parentheses 1 minus x plus delta x. On the bottom, just push all three of these factors together. Don't bother distributing. Okay, now I'm going to distribute some negatives across the top, and hopefully some things will cancel. I have 1 minus x. I'm going to get a negative 1 here, and then a negative times a negative becomes a positive x plus delta x. And since there's nothing in front of that set of parentheses, I really don't need these parentheses in the numerator anymore. So what that means is I am going to get some stuff canceling. We get our 1's canceling, our x's canceling, so all we have left is that delta x on top, which is going to cancel with the delta x that's on the bottom. So everything from the numerator is gone, so all that should be left is a factor of 1. Don't forget to have that 1 in the bottom, because what's left is in the denominator. And then finally we're ready to plug in our 0, and it's just going to go right here, and that's it. And that means what I'm left with is 1 over 1 minus x from this factor right here, and then 1 minus x with this factor. And if you want, you could write that as a quantity squared. So 1 over 1 minus x quantity squared. And that is our derivative function. So this tells me the slope of the tangent line at any x. Alright, let's try one more example here. We have the function 2 over x. So let's go ahead and start always with our limit definition of the derivative. So the derivative is defined to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So if we substitute in to our function, x plus delta x goes right where that x was. So this becomes 2 over x plus delta x minus, now we're just going to substitute in plain old x, so that's going to stay the function 2 over x. And we have another complex fraction. So just like in the last example, you want to multiply by this common denominator, which is the x plus delta x times the x. And you want to multiply by that on the top and on the bottom. So when I multiply this first fraction, the x plus delta x's cancel, leaving me this 2 and this x. When I multiply the second fraction, this time the x's cancel, leaving me this 2 and parentheses this x plus delta x. And on the bottom, just take these three factors and push them all together. Do not distribute. Now in the numerator, we still have some parentheses that we're going to want to distribute. So let's distribute our negative 2. So we'll have 2x minus 2x minus 2 delta x. So the 2x's cancel, And that means in the numerator we're left with a negative 2 delta x, and that delta x will cancel with the delta x that's on the bottom. So what we're left with on the top, don't forget that delta x term had a coefficient of negative 2. So that negative 2 is still left, and we have our x and our parentheses x plus delta x left over. We've done our canceling, so we're ready to plug in 0 for this delta x, which means what we're left with is negative 2 over x times x, or negative 2 over x squared. And that's our derivative function. That's the slope of the tangent line at any value of x. Okay, let's take a look at this example here. Find the slope of the graph of f of x equals 3x minus 2 at the point 3, 7. Now I didn't leave a lot of space here to do a lot of work, because on this particular example we shouldn't have to rely on that limit definition of the derivative if we really truly understand what it means to ask for the slope of a graph. This function right here is a linear function. It has a b or a y-intercept at negative 2, and it has a slope of 3. So up 3 over 1. So there's my graph. So if I wanted to know what the slope of the tangent line is at 3, 7, let me make my line a little bit bigger, then that would be at this point way up here. Sketch in what the tangent line would look like at that point. Well, since this is a linear function, then the tangent line at that point, the best fitting line to the line itself, would have to be the line itself. So the tangent line of a linear function is the line itself. So not only is 3x minus 2 our function, it's also our tangent line. And if we want to know the slope of the tangent line, then that's going to be the same as the slope of this linear function, which we know is 3. So without any work at all, you should be able to give me an answer that the slope has to be 3, since the function was linear to begin with, which means the tangent line will be the line itself, and so the slopes have to match. Okay? All right. Now what we're going to start looking at are some derivatives, some slopes of tangent lines that have some odd behavior. Okay, so we're going to start with the function square root of x, and we're going to find the derivative of this function, and then we're going to look at the behavior of the function itself and the derivative at the origin 0, 0. So let's start by finding the derivative of this function. And since this is not a linear function, then the only way we can find out what that derivative is going to be is by going back to our limit definition of the derivative. So that, by definition, is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And we're going to substitute in what our function is for these f's. So this input is going to go right where that x is, so our function becomes square root of x plus delta x. Then we want to subtract from that x plugged in, so that's just going to give me square root of x right back again. Now we've done one like this already today. If you have a limit that is involving some radicals, then usually a good strategy to use is to use that conjugate. So what we're going to multiply this by is the conjugate of the numerator, which is square root of x plus delta x plus square root of x. And we have to multiply by that on the top and on the bottom to keep it balanced. And I'm going to put in my parentheses to reinforce that I need to distribute or FOIL. So since this is a difference of squares pattern on the top, the inners and the outers will cancel each other out every time. So all that's going to impact our final answer is the first times the first, which is just x plus delta x without the square root, minus the last times the last. And square root of x times square root of x is just the x without the square root. In the denominator, you do not want to FOIL. Just leave that delta x out front, and then in parentheses, write that conjugate down. And what we'll see is that our x's cancel on top, which means that we're left with just a delta x on the top, which can then cancel the delta x that we have on the bottom. So don't forget, what's left in the numerator? A 1. And that means this conjugate that we had is still in the bottom. Don't try to move it up to the top. It's still in the bottom. But since those delta x's have canceled, we're ready to plug in 0 for delta x. So this goes to 0, which means we're left with 1 over square root of x plus square root of x. That's like an apple plus an apple gives you 2 apples. So this is 1 over 2 square root of x. And that is our derivative function. Okay? All right, now remember that our original function, f of x, was square root of x. And you should know the graph of that. That's just your normal square root function that goes through the origin and has that slow arcing shape. So what's the behavior of this function at 0? What's happening at 0? Well, at 0, f of 0 is still 0. It goes through the origin. Okay? So now let's take a look at what the derivative is doing at 0. So if we take f prime of x, which we just figured out is 1 over 2 square root of x, then what happens at x equals 0 here? Well, if I try to plug in 0 into that derivative, that would be giving me 1 over 2 times the square root of 0, which means we're trying to divide by 0. And what happens when you take a fraction? The numerator is constant, and the denominator is getting smaller and smaller and smaller. What does the whole fraction do? Well, when you have 1 over something small, that gets big. So this is going to blow up and go to infinity. So this is an example where the derivative at 0 is dne. It does not exist because it's blowing up to infinity. And what that translates to in terms of the characteristic you might see on the original function is that if you were to draw in your tangent line here, this graph is coming down very slowly, and I'm going to exaggerate this a little bit more so you can see what I mean. This is going to have what we call a vertical tangent line as we get closer and closer to 0. So as we travel down this graph towards the origin, those little tangent lines are getting more and more upright, more and more vertical. So what we would be on the lookout for on the original function is something with a vertical tangent line, and that would indicate to us that there's not going to be a derivative where that vertical tangent line wants to occur. So let me formalize that. We say that if the limit definition of the derivative does not exist at c comma f of c because it goes to plus or minus infinity, then the original function is said to have a vertical tangent line at c. So this would be an example of a function that might have a vertical tangent line. You can see that the graph gets really, really steep in the middle right here at c and is approaching a nice vertical line. It's very tiny, but it is getting so steep that right at c, that tangent line wants to be vertical. And that means the derivative is going to be blowing up to positive or negative infinity because the slope of a vertical line is infinite. It doesn't exist. So we say that the derivative is dne if you have a vertical tangent line in your original function. Okay? Now we're going to look at some other possible ways that the derivative might not exist. And before we do that, I want to show you or give you one more formula to memorize. This is an alternative limit definition of the derivative. And it's very useful when you're trying to find the derivative at a specific point c. So if they give you a specific value of x to plug in and look at the derivative at, this is usually the formula that I use. So here's what it is. The derivative at c is defined to be the limit as x goes to c of f of x minus f of c all over x minus c. And it should make sense why this limit definition works, because all we're doing here is we're taking the change in the y's over the change in the x's. So we're taking the limits of these secant slopes as our x gets closer and closer to c. So when you take that limit, these secant slopes turn into your tangent slope. So this is a very useful, sometimes easier formula to use. The downside is that it's only good for finding the derivative at a specific point c. So if the question said find the derivative function f prime of x, then you wouldn't want to use this. But if it said find the derivative f prime of 0 or f prime of 2 or f prime of 5, then you would want to use this instead, because it's usually much easier and user-friendly. Okay, so let's try it out on some strange functions. Okay, we're going to start with the absolute value function, absolute value of x. And for all of these examples, I'm going to ask you to find the derivative at 0. So we're finding the derivative at a specific point. Here our c is going to be the 0. So here's how this new definition works, this alternative limit definition. It says that the derivative at 0 would be defined to be the limit as x approaches 0, because c is 0 in this problem, of f of x minus f of 0 over x minus 0. So all I did was use this formula, plugging in 0 for c. Now we need to plug into our actual function itself. So if we take a look at our numerator, we need to know what f of x is, and f of x is just absolute value of x. That's how it's defined. And then we would need to know f of 0. So if you plug in 0 into this x position, that would be absolute value of 0, which we know is just 0. So this goes to 0, this goes to 0, which means what we're left with, what we're really trying to find the limit of, is absolute value of x over x. Now that should look somewhat familiar to you from when we talked about limits in the past. This is called the Heaviside function, and it is a step graph. You want to have this graph memorized. When x is positive, this always reduces to 1. When x is negative, this always reduces to -1. And it's not defined at 0 because you can't divide by 0. So I have 2 open circles on my endpoints. So this is the graph of absolute value of x over x. So what would be the limit of this as x goes to 0? We can't just plug in 0, because that would give us our indeterminate form, 0 over 0. So the only way to figure out this limit is to do it graphically, to look at this graph and figure out what's the limit. Now, since there are different pieces, we are going to have to look at this from the left and from the right. So the limit from the right side of 0 means that I'm traveling in this direction towards 0, and all of those y values are always 1. If we come from the left side of 0, then we're traveling in this direction towards 0, and all those y values are -1. So that means the two-sided limit does what? Well, since the left-hand limit was -1 and the right-hand limit was +1, and these do not match, then the two-sided limit is d and e. Okay? So, couple of comments here. This graph that I have here is actually the graph of the derivative function. What's the graph of the original function? You have to keep these straight. So this is actually our f prime of x. What's the graph of f of x looking like? Well, it was the absolute value function. And you should know what that graph looks like as well. That's just a great big V centered at the origin. So what characteristic of this graph could we have looked for to predict that there wouldn't have been a derivative at 0? What is happening at 0 on this graph that tells me that there's not going to be a derivative at 0? Well, what's happening is you have this big V, right? And in calculus, we call that a kink. We have a kink in our graph at x equals to 0. And if there's a kink in your graph at whatever point, then that means you are not going to have a derivative. So in this problem, f prime of 0 was dne because f of x had a kink at 0. And think about why that would result in a do not exist derivative. If you visualize all these tangent lines from the left side, they are all just like those lines itself, which have a slope of -1. All these -1 slopes right here. On the right side, all these slopes are 1. So how can the graph suddenly go from a slope of -1 to a slope of +1? It can't just jump right to that new value. You have that kink in the middle, which is what's causing that big jump in your derivatives. So the fact that you have that sharp turn is what's causing you not to have a derivative. So look for that on your graphs. If you see a kink, then you'll know right where that kink happens, there can't be a derivative. The derivative will be dne. All right, let's try another example of a derivative that does not exist and find out why it doesn't exist. So this time we have, for our original function, the greatest integer function, and you should know what the graph of that looks like. That's just our step function. Each step has a width of 1 and jumps up by 1 each time. The right endpoint is open, the left endpoint is closed. So that's what the function itself looks like. So right at 0, it's going through the origin. Now let's see what that implies about the derivative at 0. So to find this derivative, I'm going to go back to my new alternative limit definition of the derivative, which is good for finding the derivative at a specific point. And we are being asked to find this derivative at 0. So I'm going to let c be 0 in this formula. So according to this new limit definition, f prime of 0 will be the limit as x approaches 0 of f of x minus f of 0 over x minus 0. And now we're actually going to plug in our function. So f of x is this greatest integer function. What is f of 0? Well, the greatest integer value of 0 is 0 itself. So if I plug in 0, I'm going to get 0 back. So this becomes the limit as x goes to 0 of the greatest integer function x over x. Now, because the greatest integer function has this step characteristic, you are going to have to look at your left hand and your right hand limits separately, just like we did on that last example with the Heaviside function. So here, let's take a look at what's happening from the left side of 0 and the right side of 0. So if I look from the left side, here's the graph of the greatest integer function right here. We're going to refer to that. We're going to take the limit of the top separately over the limit of the bottom separately. So we're not going to look at the graph of this whole ratio. I don't know what the graph of that looks like off the top of my head, but I'm going to find the limit of the numerator and divide that by the limit of the denominator. So in the numerator, what would be the limit of just the greatest integer function of x if x is approaching 0 from the left side? Well, here's 0 from the left side means I would be on this step down here. And what would all those y values be going to? Well, they're going to -1. So the numerator in the limit is going to -1. What's the denominator going to? Well, since it's just x in the bottom and x is going to 0 through negatives, then this would be going to 0 through negatives as well. So think about what that's doing. That's a constant over something getting smaller and smaller and smaller. So that means this is going to get bigger and bigger and bigger as a fraction. 1 over something small gets big. And since you have a negative over a negative, this is going to positive infinity. So right away, I'm going to stop. If you wanted, you could go ahead and look at the right-hand limit as well, but you don't need to, because you already know that the left-hand limit doesn't exist. So there's no way that the two-sided limit can exist if one of the side limits, the left or the right side limits, doesn't exist. So this is going to tell me that f prime of 0 must be dne as well. Okay? So since the left-hand limit was dne, then the two-sided limit, which is our derivative, must be dne. So that's our answer for what the derivative is. However, let's see what characteristic is it that's going on here that's making that happen. What's happening at 0 here? Well, we have this big jump, right? We have this discontinuity right at 0 because our graph is doing something from the left differently than it is from the right. So one thing that you want to look for is that the derivative, you know, will be dne because the original function is discontinuous at x equals to 0. That wasn't the case over here. This was a continuous graph. It's nice and smooth. You can draw the whole thing without lifting up your pencil. It was the fact that it had a kink at 0 that led us to know that we wouldn't have a derivative at 0. This one has a jump at 0, a discontinuity, so that's what's telling me that I know the derivative won't exist. Okay? All right, one last example, and then we'll summarize everything that we've just discovered. So this last one is the function x raised to the 1/3, and you want to remember that the 1/3 power means a cube root. So the graph of x to the 1/3, which is the same as the cube root of x, hopefully you know what that looks like. It's kind of a big, flat, sort of S shape like this, and it goes right through the origin. So let's go ahead and see if we can find out what the derivative of 0 is going to be. Using our new alternative limit definition of the derivative, this is going to be the limit as x goes to c, or x goes to 0, of f of x minus f of c, or f of 0, over x minus c, or x minus 0. So if we plug into our function, f of x is x to the 1/3. F of 0, if I plug in 0, the cube root of 0 is still 0. So these two guys go to 0. And what we have now is x to the 1/3 over x. Now let's use a little bit of our exponent laws, our laws of exponents here to simplify this, because we have x's on top and bottom. So we should be able to combine those x's into a single x term. Since the power on the bottom is an implied 1, if you have the same base on the top and the bottom, what do you get to do with their exponents? You get to subtract. So if I subtract 1 minus 1/3, that's going to give me 2/3. But that answer's got to stay in the bottom where that bigger power is. So in other words, x to the 1/3 over x reduces to 1 over x to the 2/3. Now let's take the limit of this. The numerator is constant. It's always 1. The bottom is going to 0, and it's going to 0 through positives because we are squaring that cube root of x. So this is going to blow up and go to positive infinity, which means that the derivative at 0 is dne again. If your derivative is infinite, then that's going to be dne. Doesn't exist. So what we're trying to see is what characteristic of this original function, this original graph, could have led me to know in advance that this derivative should have been dne from the start. And we talked about this earlier today. You can see that nice flat S shape has a very steep part to it right at the origin. That's where it gets its steepest. And so the tangent line right at 0 wants to be vertical, wants to be straight up and down. And the slope of a vertical line is infinite, 1 over something getting really, really small. So that's why this is dne. So the derivative is dne because the original function f of x had a vertical tangent line at x equals to 0. So what I'm trying to give you on these three examples are three things to look for. It's tedious and messy to have to compute these limit definitions of the derivatives. So if you can just look at a graph and know that it has a kink, or it has a discontinuity, or it has a vertical tangent line, then you'll know right off the bat that the derivative is d and e. And you won't have to go through all this work of trying to calculate it. So that's what this summary is on the next page. We say that a function is not differentiable at a point C if at that point there is either a kink or a sharp turn, like we had right here at the V, a discontinuity. Now a discontinuity could happen any number of ways. You could have a discontinuity due to a jump, you could have a discontinuity due to a hole, or you could have a discontinuity due to a vertical asymptote. So if you see any of those things happening in your graph, then you know you're not going to have a derivative there. And finally, if you have a vertical tangent line, and that would be the case where your graph is getting very, very steep at some point, and there wants to be a vertical tangent line there. Okay? All right. So what is it that's causing these three things to not allow us to have a derivative? If you were to take, for example, this great big kink in your graph, this great big absolute value function, remember what we said earlier, that a tangent line is supposed to fit the direction of the curve and sort of approximate the curve if you were to zoom in enough. And this is a property of being locally linear at a point. We would say that a function is locally linear at C if you can zoom in enough near C so that f of x becomes linear. And that line that f of x is becoming is your tangent line. So consider this absolute value. If I zoom in at the origin, is this ever going to look like a straight line? No, because there's no way to get rid of that little kink in your graph. So this particular graph is not locally linear at the origin, at 0, which implies that there is no derivative. If you're not locally linear at a specific point, then you're not going to have a derivative there. If you are locally linear at a point C, then you will have a derivative there. Okay? So let me just show you a quick little video here to demonstrate that. So here's our curve. Our function is in purple, and this tangent line you can see is in that blue and yellow. And when I click on this graph, what it's going to do for us is it's going to show us the graph zooming in and zooming out. So if I click, you can see that the graph is zooming in, zooming in, zooming in. And what's happening between that purple curve and that tangent line? Now we're zooming out, so they're coming farther apart, and as I zoom in, they get closer and closer and closer to each other. So the more you zoom in, the more that purple curve looks like a straight line, the more it looks exactly like that tangent line. And that's the property of being locally linear. If you can zoom in enough on your graph to make it look like a straight line, then it has a tangent line, which means it has a derivative. Okay? All right, so here's a theorem to summarize. If a function f is differentiable at x equals to c, then it has to be continuous at x equals to c. Okay? If the graph was not continuous at c, then it certainly doesn't have a derivative there. And we saw that up above here when we talked about these discontinuities. Okay? So let's put into practice this theorem and see if we can understand all the little nuances. Suppose that you have the function y equals the absolute value of x minus 1. Think about what the graph of that looks like. It's an absolute value, so it's a V shape. And because of that minus 1, that's a transformation, which is a shift right 1 unit. So this is a V centered at 1. First question, is that continuous at 1? Yes. You can draw that entire graph without ever once having to lift up your pencil due to a jump, a hole, or an asymptote. Question 2, is this graph differentiable at 1? No, and that's because it has a kink at x equals to 1. Now let's be a little bit more general. Suppose that a graph is discontinuous at C, then it is not differentiable at C. True or false? If a graph is discontinuous, then it is not differentiable at C. Well, we know that if you have a discontinuity, then you're not going to have a derivative. So this is true. Okay? How about if a graph is continuous at C? Will it have a derivative at C? So if a graph is continuous at C, then does it have to be differentiable at C? That is false. And an example or counterexample to that would be this graph right here. This is continuous at 1, but it doesn't have a derivative at 1. How about if a graph is differentiable at C, then it is continuous at C. So if a graph has a derivative at C, must it be continuous at C? Yes, it must. This is true, and that's exactly what this theorem is telling us right here. If you have a derivative at a point, then the function must have been continuous to begin with. So here's the nuances. Differentiability, and that just means having a derivative at C, implies continuity at C. So if you're differentiable, you must be continuous. But it doesn't work in the other direction. So continuity at C does not necessarily imply differentiability at C, because there are many continuous functions like this V shape right here that are continuous but aren't necessarily differentiable, because maybe they have a sharp turn in them, maybe they have a vertical tangent line, something like that. Okay? All right, let's summarize all of the derivative formulas that we've talked about today. If you want to know just the derivative function, so f prime of x, so you're finding the derivative at any point x, then I would recommend using this limit definition of the derivative. F prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And your final answer here will be a function with x's still in it. If you want to find the derivative at a specific point C, like f prime of 0 or f prime of 2 or f prime of 4, then I would recommend using this alternative definition, where you take the limit as x approaches your C of f of x minus f of c all over x minus c. Now you don't have to do it that way. You could use this formula up here and plug in c at the end. That's okay too. But usually I find that this alternative formula is a little bit easier and more user-friendly. So I tend to use this one when I know that I'm looking for a derivative at a specific point, and I use this one if I want the derivative at just x. Okay? These are formulas that you need to memorize. Okay? One other common thing that you're going to be expected to do is to find the equation of a tangent line. So here are the steps for doing that. You can use either of those two formulas, but I would probably recommend using this alternative form, since if you want the equation of a tangent line, that means you're looking for a slope at a specific point. So why not use this derivative formula for a specific point C? So I would first calculate this f prime of c using this alternative form, and that's going to become your slope m. Then you're going to need to find f of c. That'll be your y value of your tangent point. Sometimes they'll give that to you, sometimes they won't. If they just give you x, then you need to take that and plug it into your function to find the y. Once you know your y and your slope, then you're just going to plug it into your point slope form. And this is, again, something you want to have memorized. And this is basically your y minus y1 equals m times x minus x1, where the point that you're plugging in is that c comma f of c, and the m that you're using is what you got when you used your alternative definition to find your derivative. Okay, so these are all things you're going to be expected to know how to do. All right, this is a long, tough lecture, so hang in there. We're almost done. However, this last thing that we're going to talk about can be a little bit tricky. What we're going to do is we're going to find derivatives, but we're not going to be able to do it using formulas, because in these examples here, I'm not giving you a rule for f of x. I'm just giving you a graph of f of x. And based entirely on that graph, I want you to sketch what the derivative should look like. Okay, so there's a process to this, and I'm going to try and give you some hints for how to make this go easier, but it does take practice. So the more of these you do, the better and easier they're going to get. But you will need some time to kind of absorb the information, practice it a little bit before it starts to sink in. So let's take a look at this first graph right here. This is the graph of our f of x. And what we want to do is graph what f prime of x should look like. And the only way we're going to be able to do this, since I don't have an actual formula, even though you could probably guess what it is, this looks like the absolute value function, but what we're going to do is we're going to figure out these derivatives by sketching in little tiny tangent lines. And these tangent lines should look like little linear approximations to the curve. So take your pencil, it's good to use different colors here, and just sketch in what little tiny line segments would look like that would represent these tangent lines. So if I draw little tiny tangent lines, all of these tangent lines on the right hand side look exactly like that line itself, because the original function is linear over here on the right. And what is the slope of each of those little tangent lines? Well, it's going to be the slope of whatever this line is. And this line goes up 1 over 1, so it has a slope of 1. So what that means is that my tangent line slope is 1 for all of these x values. So when the x is 1, the slope is 1. When x is 2, the slope is 2. When x is 3, the slope is, sorry, I said that wrong. When x is 1, the slope is 1. When x is 2, the slope is 1. When x is 3, the slope is 1, and so forth. So how we're going to show that is that we're going to graph, I'm going to use blue for my derivative here, I'm going to graph for whatever x values these correspond to. The y value that I'm going to be plotting is the actual slope of these little red tangent lines. And these y values are all going to have values of 1, since all these slopes were 1. So I have all these 1s for all those x's, and it would also be 1s for all the decimals in between. So for this entire right hand side, the slope is constantly 1. So you get this constant horizontal line at a height of 1. Now let's do the same thing, but on the left side. So if I sketch in all of these little tiny tangent lines, what are the slopes of all of those lines? Well, they go up 1, left 1, so the slope on the left side of the graph is always negative 1. So for all these negative x's, my slopes are always negative 1, constantly negative 1. So we get a nice horizontal line, but it's at a height of negative 1. Finally, to finish off the graph, what happens right at 0? Well, right at 0 is that kink, and we know that you don't have a derivative if there's a kink in your graph. So to show that, I'm going to put an open circle on each of these two endpoints so that I make sure not to include it. So there's actually no value being plotted at 0 because the derivative doesn't even exist at 0. So this graph in blue is now my derivative function. So the slopes are always 1 to the right and always -1 to the left, and nothing, D&E, at 0. So I didn't plot anything at 0. Okay? Alright, let's try it again. Again, these take some time to kind of get used to. So what I'm going to do on this next graph is I'm going to draw in those tangent lines again. Now, one of the things I always look for are tangent lines that are nice and flat, nice and horizontal. And hopefully you can visualize. I'm going to draw in a few of these tangent lines, and they're all just little tiny line segments that are approximating the curviness of the graph. That's what a tangent line is. It's a linear approximation of your curve at that point. So if we draw in all of these little tiny line segments, where are the flat ones? I have a horizontal one here, horizontal here, horizontal here, horizontal here, and horizontal here. What's the slope of a horizontal line? 0. So at this x value, which is at 1/2, I want a slope of 0. So that's going to be, actually let me use a different color here. My derivative for the y value that you're plotting is the slope of that line. So at this x value, the slope should be 0. So I'm going to be plotting a point with a y value of 0. At this x value, the slope is 0. So I want to plot a y value of 0 there. At this x value, the slope is 0. At this x value, the slope is 0. And at this x value, the slope is 0. So I always try and plot my horizontal slopes, my 0 slopes first. And then in between those zeros, I figure out what my slope is doing. Okay? So let me take away some of these marks so that we can see what's going to happen in between these 0 slopes. So let's take a look at what is happening between this 0 and this 0. And you have to look at this carefully. This very first slope that I'm drawing, notice that it's positive because my graph is rising up. And then it's a little bit more steep, a little bit more steep, and then it's going to have to start getting less steep so that it can eventually get back down to that 0 again. So if we plotted those as actual points, this first slope right here is a little bit positive, and then my next slope is a little bit positive, and a little bit more positive, and right when I get in the middle there, right at when x is 0, I'm kind of at my steepest point. And then my lines start to get more and more horizontal to get back to that 0. So the slopes have to get less and less large. So they have to get smaller and smaller and go back to 0. So what happens is we have these slopes going up, up, up to that peak, and then they have to turn back around so they can come back to 0 again. Alright, let's try that again over here. So when I draw this first tangent line, what kind of a slope is that? Is that a positive slope or a negative slope? Well, it's negative because the graph is falling. So for that little x value, which is just to the right of my 0 slope, I've got a negative slope, and then it gets more negative until the middle, right about 1, it gets sort of its most negative. And then the graphs of these little lines have to sort of level out again to get back to that 0. So these slopes have to come back around to hit that 0. So my slopes go down and then they go up again. If I go to the right side of this horizontal tangent line, I have a positive slope again, more positive, and then right in the middle at 2, I'm my most positive, and then I have to get more and more horizontal to get back to that 0. So these slopes go back down again to get back to 0. Over here I have a slightly negative slope, then a little bit more negative because it's a little bit more steep, a little bit more steep, a little bit more negative, and then right at 3 I'm at my most negative, and then I become a little less steep, a little less steep, a little less steep, a little more horizontal, so that I come back to that 0. And then over here I'm back to positive, 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 more positive, and then sort of maxing out at about 4. Over on this side, I'm a little bit negative, a little more negative, a little more negative, a little more negative, and sort of maxing out there at -1. So this graph in blue would be my derivative function. Okay? So these are tricky, but start with those horizontals and then visualize what's happening to your slopes. Are they starting out positive or are they starting out negative? And then are they getting more steep or less steep? Are they getting closer to horizontal or more and more vertical? Okay? Let's try it again. So this time I want to graph not only the derivative f prime of x, but now we're going to graph something we haven't even talked about, f double prime of x, and this is called your second derivative. So that's just the derivative of the derivative. So once we get the graph of f prime of x, we're going to do the same process on it to figure out what the derivative of it would be, and that's going to be called our second derivative. So let's start by first finding our first derivative. So look for those little tiny horizontal tangent lines. Horizontal, horizontal, horizontal. Notice they're going to happen at those little peaks and valleys, those maximums and minimums. Everywhere else, your slope, your tangent lines are going to be angled, either up or down. So everywhere else, we don't have to worry about it. But when you have a peak or a valley, you should be getting that horizontal tangent line. So I have a minimum right here, so that's going to correspond to a 0 slope. I have a maximum right here, which is going to correspond to a 0 slope, and then another horizontal tangent line, which is another 0 slope. Alright, now let's look at the slopes in between those zeros. So let's start. It doesn't really matter where you start. Let's say that I start at this first 0 and I go towards the origin. So here's my first horizontal tangent line right there. And then the next tangent line is just angling up just a little bit to the right, so it's rising up. So that's a positively sloped line. Then it gets more positive, and then about halfway through, it has to start leveling out again so that it can come back and become horizontal again. So this is just going to go up, up halfway, and then it has to come back down again to get to that 0. Now on the other side of 0, we start with a little tiny tangent line. See if you can see that. That's a little bit negatively sloped. It's falling. So this is going to go slightly negative. It's going to get a little more negative as I progress, and then about halfway through, it's got to turn back around, and these tangent lines become flatter and flatter and more horizontal to get back to that 0 slope. So this is what we have going on in the middle. After this horizontal, I'm back to a little positively sloped line, then it becomes more steep, more steep, more steep, more steep, more steep, more steep, and it doesn't appear to be flattening out. I don't have any more maximums or minimums after this point because I have that arrow. So these slopes are going to start out positive and just continue to get more and more positive. So this graph is going to continue to go up, 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 just like that. On the other side over here, this first little slope, it's falling, right? It's decreasing. So this is starting out negative, and then it's a little more steeply negative, a little more steeply negative, a little more, a little more. As these become more and more vertical, that means your slope is just getting bigger and bigger, but in the negative direction. So these are getting larger and larger, but in the negative direction, like that. So this graph in blue is my f prime of x graph. Alright, now let's repeat that whole process again, but now we're going to do it on this blue graph. We're going to take the derivative of this blue graph, and that will be what we call the second derivative. So let's look for the peaks and valleys of this blue graph. I have a maximum right here, which will have a 0 slope, and a minimum right here, which will have a 0 slope. In between those two, this little tiny tangent line here, notice it's falling. So I have a negative slope, then it gets more and more negative till about halfway, and then these slopes have to come back around to hit that 0 again. So you're going to get that little U shape where it goes down, 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 but then it turns back around so that I can hit that 0 again. After this 0, this slope is positive, positive, more positive, more positive, steeper, steeper, steeper. So these are just going to get more and more positive and go up like this. On the other side, I have that 0 slope, and then this very next tangent line would have a positive slope because this little tangent line is rising up, and then these are getting more and more steep, but they're getting steeper in the positive direction. So these are going to be slopes that are getting more and more positive going up. So this graph in red is what we call the second derivative. And if you look at your graph's shapes and you know a little bit about polynomials, the very first graph we started with looks kind of like a W, and that's typically the shape of something like an x to the 4th. The next graph that we did in blue has sort of a cubic shape to it, and then the last graph that we did has sort of that quadratic shape. And so you can use that to kind of help check that you're doing things correctly. Each time you take a derivative, the degree of that polynomial goes down by 1. So we went from an x to the 4th to an x cubed to an x squared. So that'll just give you a way to sort of double check that you're doing things correctly. Alright, let's try this last one here on this page. So we're going to find the first derivative first. So what we're going to do is look for those peaks and valleys. I've got a nice maximum right here, which is going to have a 0 slope at that corresponding x value. And then here, this kind of levels off right about here. So I'm going to have a 0 slope there. And that's not, it's kind of a little tiny max, but it's also sort of a flat spot in our graph. So those are the only little level spots that I see for my tangent lines. Now, if we go to the left here, this is a little positively sloped line, and then it gets more steep, more steep, more steep, more steep, more steep, more steep. And these are all positive. So I start out with a positive slope, so I want to be going up in the positive direction. And then they're getting larger and more positive slopes. So this is going to go up, 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 just like that. On the other side of this horizontal tangent line, this very first tangent line is falling, it's decreasing. So that's going to have a negative slope, then more negative, more negative, more negative, and then it has to start flattening out again and getting more horizontal so that I can get back to this 0. So this is going to go down, down, down until about halfway when it has to turn back around again so I can get back to that 0. So this is going to have a shape like that. And then after this flat spot, I'm back to another negative slope, more negative, more negative, more steep, more steep, more negative. So this is actually going to come back down and keep going down like this. So this graph is going to do something kind of like that. Let me see if I can smooth it out a little bit. So we touch that 0, and then we bounce off and go back down again, because these are all negatively sloped lines. So I want to see all these y values, which represent the slopes, should all be below the x-axis, because all these slopes were negative. So I shouldn't see any y values above the x-axis for this region. Okay? So this graph in red is our first derivative. Now we're going to do the same process on it to find the second derivative. So do we have any maximums or minimums? There's a little maximum right here, so that's going to have a 0 slope at that x value. And I have a little minimum here, so that's going to have a 0 slope at that x value. And you just want to estimate here. I mean, these aren't going to be exactly the right thing because we don't have enough information about our function to know exactly what these slopes are. We're just doing a rough sketch to get a feel for what the shape should look like, and that's the best you can do for these. Now let's look between these two zeros. This is a little positive slope, a little positive. In the middle, it reaches its most positive, and then it has to level back out again to get back to that 0. So these are all positives, so I should be plotting positive y values that go up till about halfway, and then it has to come back down again to that 0. So you're going to see that shape to it. After this peak, these are negative slopes that continue to get more and more steep. So they're going to continue to get more and more negative. So something like this. And to the left of this 0, this is a line that is falling as well. So it's going to be negative slope, negative, more and more negative as these get steeper and steeper in the negative direction. So this continues to be negatives as well. So you're going to get a graph that looks kind of like a quadratic shape but pointing down. And that's the graph of our second derivative, f double prime of x. Alright, now based on what we just talked about, can you look at these two graphs and determine which graph is the original function f of x and which graph is f prime of x? Well, look for those horizontal tangent lines to help you out. This curved shape, which almost looks quadratic, has a minimum right at 2, which corresponds to a 0 slope, which just so happens to be this line. All of these slopes to the right are positive, which corresponds to these positive y values here. All these slopes to the left are negative slopes, which corresponds to these negative y values here. So that means the curvy one is the original function f of x, and the line are all the slopes, which means it's the derivative function. Okay, and you can also do a quick check, like I was mentioning before, by thinking about degrees. This curvy function looks kind of like a quadratic, like an x squared, and 1 degree less than that would be linear, which is this line. So it makes sense that we've chosen f of x to be the thing that looks quadratic and f prime to be the thing that looks linear. Okay, last problem and then we're all done. We're going to find the derivative of this crazy graph. Okay? So there's lots of stuff going on here. If you want to start by looking for those 0 slopes, that's a good place to begin. So you're looking for peaks and valleys, things like that. And also we have some strange behavior going on. We've got some discontinuities because we've got some jumps. Notice here at the origin, or excuse me, at 0, 1, we have a kink in our graph, and then we have another graph or another jump over here as well. So if we start by looking at some of our slopes of our tangent lines, over here you can kind of see that nice peak. So right at about 2, it looks like we have a 0 slope. To the right of that, this is a negative slope, negative, more steep, more steep, more steep, and it just keeps getting steeper. So this is going to go more and more negative all the way down. So this has got to do something like that. On the other side of that horizontal, you start out flat and then you get a little tangent line that sort of rises up here. So that's a positive slope, more positive, more positive, more positive, and then it just kind of abruptly stops right at that open circle. So this is going to go more and more positive until we get to the x value of 1, and then it abruptly stops. Now, does the derivative exist when x is 1? And the answer there should be no, because you have a discontinuity, you have a jump. So we need to put an open circle on the end of that so we don't include it in my derivative. Okay, now let's look at this this little diagonal line segment right here. If you draw in your tangent lines right here, what slopes do they have? Well, this is a straight line. So whatever the slope of that line segment is going to be the slope of all of these tangent lines. And since this goes up 1, left 1, that's a -1 slope. So for every x between 0 and 1, all of these slopes should be -1. So for all of these x's, I want y values that are always -1. So this is going to be a horizontal line segment. And because we have that jump right at 1, you want to put an open circle on the end of it. Because we have a kink right at 0, you want to put an open circle on the left side as well. Now on the other line segment on this side, these little tangent lines are going to look exactly like that line, and that line has a constant slope of +1 because I go up 1 over 1. So for all of these x values, I want to have a constant slope of +1 up here at a height of 1. The endpoint at 0 should be open because of that kink. The endpoint at -1 should be open because of this jump discontinuity. Okay, and then finally, this horizontal line segment, what are the slopes of each of those little tangent lines? Well, since they're all horizontal, slopes of horizontal lines are always 0. So every single one of these x values should have a y value slope of 0. So these are all going to be zeros. And you want an open circle on the end of it because of that jump discontinuity. So let me clear out some of my little marks here so that you can see what we have more clearly. So this graph in red is the graph of my derivative function. And every place that I have an open circle means the derivative does not exist there. Okay? All right, that concludes our lecture on the derivative and the tangent line problem. Good luck.